Today I'll show you a demo of some stuff we've been working on and particularly related to video data management. It's been a requested feature by some of our customers, and it's a very interesting way and very powerful way to manage video data, which expands on telemetry data, but is also much larger in size. And so we've created this very powerful solution for you to manage your data efficiently without needing to centralize video. So what I'm showing here is a diagram of the demo I'm going to show you today. So we have two video cameras, and each of these video cameras is pushing live video streams to an edge node running EdgeLake. And on this EdgeLake node, there's a SQL database and also an object storage database. And so the object storage database is just a standard MongoDB Docker container. And what I'll show you is that when video stream to EdgeLake, we process that video, and we also have an AI model that sits on the edge device, and it runs inference on every single frame that's streamed by the video camera. So now when video comes into EdgeLake, AnyLog executes inference on the frame, and it writes the inference telemetry to a SQL database, and it also writes the video file to an object storage database. So that would be MongoDB. But what this allows you to do is it allows you to query your AI inference through a metadata-rich discovery. So typically when you store your videos in object storage, you're kind of limited based on either the prefix that you write the video to, or the database, or the table, or the file name. But now what we've allowed you to do is query this video files using the telemetry that was created by the AI model. And then as the video is being streamed to two different EdgeLake nodes, I'll show you how we can query the videos and the telemetry as if the video data and the telemetry were stored in a single logical system. So applications and your monitoring queries what we call an edge data fabric. And this creates you a unified view of all the data as if it was in a single centralized database without all the complexity of having to move the data from the edge node to the cloud. So one of the value propositions here is that data remains in place. The same model we presented earlier with EdgeLake, where you keep telemetry data in place in localized SQL databases, it now applies to also video data and blob data. And so we basically expanded the power of EdgeLake to support the blobs and telemetry. So I'll transition here to the AnyLog GUI, or to the EdgeLake GUI as well. This is a GUI interface that comes standard with any deployment. And within this, we've expanded the GUI to support a video stream viewer. And so as we click here, I see all my videos that are coming to life. So I have operator one, so I have an edge node one, and I'm streaming a live stream of New York City Times Square. On the right here, I have a live stream of a traffic camera from Caltrans. So this is actually a live video stream as well from Santa Cruz, California, of the on-ramp coming into Santa Cruz. And every frame that's coming, there's an AI inference happening by EdgeLake, and every green square here is now being written to the localized SQL database of the EdgeLake operator as a row in the database. And so we're keeping track of the number of people, the number of cars, the number of buses, and the number of trucks in this specific demo. So we can see the AI model referencing this. But what I want to emphasize here is that there's two nodes, but I get to view the video data as if it was on a single centralized machine. So this scales horizontally. I can add more and more nodes, but my view of the video data as if the video is being centralized to one instance. So now that I have the video streams, we can also start querying the data and start running analytics against the video streams. So if I go to our client dashboard, we can run some SQL queries to access this data. So for example, I can run the SQL query. I can make this a little larger. All we're asking here is select the file, the timestamp, the car, the truck, bus, person from a table from over the last 5 minutes. And when I hit send, we can see that we get data from operator one. And if we scroll further down, let's run this again. Operator one is having a lot of data. So there's data from two nodes. Let me, um, okay, so operator one is hogging the rows that are coming back. But nevertheless, what we see here is that we have data coming in from operator one, and we see the row as well. And so we can see in this specific frame, there was two cars, three trucks, and zero buses, and zero people. And we can query this data from this. And if we wanted to see this video, we do the same thing. We basically have created these pointers to the object storage. And from the same query, we can view the blob data. So we can use our video player, and we can see that we can bring the video back as if the data was on a centralized device. So here we're getting a 3-second shortened clip of a 1-minute video frame that we had earlier. And the thing that I'll show you next is we can also run aggregation. So here we're running the average. So the average number of trucks, buses, and people in the frames over each minute frame. So we can see also more videos from operator one and operator two. And so what I'm showing here is that we're running aggregation on the telemetry. So we can see that operator one on this specific video clip, in the 1-minute clip, there was 496 inference results. And across those inference results, there was an average of 4 cars, 0.63 trucks, 0.07 buses, and a small number of people. And in the Times Square, we can see that there's a little bit more vehicles happening. So we can see there's 4 cars, fewer trucks, but a lot more people in our Times Square video stream. But the power of this is not just running queries against the telemetry, it's also bringing the video back directly to the browser as if all the video data that was stored on 2 different nodes was in a single machine. So here I'm bringing 2 videos from each operator. And if we hit the view blobs button, we can look at the player and we can see here's a Santa Cruz, California video stream that we requested. Here's the Times Square video stream that we requested. And this is all shortened. So this is coming back to the browser. So we're querying the data and streaming it back to the browser. And here's another Santa Cruz stream that we brought back, and it's just buffering. And here's another video of Times Square at a different time. So we can see it's a lot busier at this point. And so again, the value here is that we've expanded video blob retrieval to not just be based on prefix or file name, but really what you can do now is endless. You can query the video data back through telemetry data and through standard SQL. What it allows you to do is you deploy EdgeLake, you stream the video to the EdgeLake node, and that's it. Before, you would have to figure out how to stream the video to some edge node and from there forward it to a cloud instance or another node. And how do you display the videos in a nice way, in a nice chart? Here, what we can show you is you can just take the streams. So here, what you can do is you can take the stream. So here, this is an EdgeLake node streaming the video and offering me an endpoint to view the data. But now what you can do is you can create your own dashboard dynamically to view all the videos. So you can just start putting video streams here and then organizing it in a single way, in a single logical way that makes sense for your use case. And that's it. So there's the simplicity is the key value here. And also the AI. So you don't need to start organizing where the AI model goes. EdgeLake does that all for you. You just define the endpoint and EdgeLake executes the inference for you and writes the results to a SQL database.
So, Roy, is this essentially eliminating the old idea of creating a video pipeline?
Yeah, that's our claim, and that's where
Yeah.
I think we're showing. You can stream more than one. video stream to one EdgeLake node. The limitation there is the capacity and the resources that the Edge node has. So more video streams requires more resources, but there is no limitation to how many nodes you can run. It's a question of what the resources are, not what EdgeLake can do. So right now the AI is sitting directly on the EdgeLake node, on the Edge node where EdgeLake is running. But another way to run this setup is you dedicate another edge node here that's that's sitting next to your edge lake nodes. This AI node is running a GPU, and the edge lake nodes are sending the frames and retrieving the inference results. And same for this node here. So it sends the frame to the AI node and it retrieves the inference results. And that's one way to enable more scalability on the AI side. On the other side, you can also have more cameras here and more cameras streaming to your EdgeLake devices as well. The question is what are the resources? And if the resources allow for more compute resources that video takes, then EdgeLake will be able to handle it as well.
So the AI node, and there could be multiple. You don't have to
Yes.
work with one, and you could put nodes with GPUs or optimized. Can you talk about the AI that runs? What is this AI and what's
Yeah.
because people have or companies have different logic that they want to implement on their video feeds.
Yeah. So the AI that we're running here is standard YOLO model, and we've actually created a GitHub repository for you to try this yourself as well. And so essentially just git clone this link. And if you run makeup dash GPU, it'll run a Docker container with access to the machine's GPU, and it will run inference and expose an endpoint that you can send video frames in, and it will give you the inference that the YOLO model produces. So a YOLO model, and just for context, a YOLO model is an AI model that is pre-trained and basically detects different objects that company that built it has trained for. So the common use case for it is to detect objects like trucks, people, stop signs, light poles, other traffic signs, and things of that nature. And we're using this model in the demo to pick up people and trucks and buses. But you can try this model, and I Dockerized this deployment. And if you want to run on a machine with a GPU, you do makeup GPU. And if you want to just run without a GPU, you just do makeup, and it'll work automatically. So within EdgeLake, we made the decision to execute the inference through gRPC. It's a little bit faster than standard REST, especially because the frames are coming in at something like at least 36 frames per second. And so what you do is you define a gRPC endpoint using this command, this EdgeLake command. So run gRPC client, where the name can be anything you want. And then this is the IP and port of your gRPC model. And then you provide us the proto files of what they are. And specifically, we've defined that we need a function name called predict stream. And you send your request through a predict request naming convention. And your response that you expect is predict response. And essentially, if you build a gRPC endpoint that can satisfy these restraints, you can deploy your own model and EdgeLake will be able to connect. We're working on making this more modular, but for the time being, this is the way you can connect to your AI model is through gRPC and defining a proto file that satisfies a function called predict stream, has a request type predict request, and takes a response called predict response.
The idea is to allow companies just to plug an AI and satisfy a get and a response call, and that should work with EdgeLake instances that could be distributed all over the place.
This documentation is also available. If you go to the AnyLog documentation on GitHub, it's just under video streaming, and you can try this demo yourself, and you should try it with Mark's OVA build.
A quick question for Roy. As far as the video operation, if we're operating in a continuous flow manufacturing and we set up to watch the processes. We're looking for not just specific counts of different types of objects or that sort of thing, but for behaviors that may be anomalous. Is that a good thing to pursue with the approach that you have here?
Yeah, so if you wanted to detect anomalous behavior, it's the thing that changes is what your model outputs, right? So we can capture that information in telemetry and you can query the anomalous behavior via SQL. So if we can define a structured way to capture that information and write it to a SQL database, then we can also query it via SQL and you can get that use case that you need.
One thing I can add to that is that I know that it's very common for factories to deal with operators using hard hats, and I know IBM has worked on attempting to create a model that's specifically for that and those types of issues. And so you just need to find the right model to match your criteria, and then we can easily, as Roy mentioned, store the data and store the insight about usage of a hard hat for sake of argument.
It sounds like what you're describing is that you have an opinionated way of solving the problem. Plus, it sounds like this, because you have a pipeline replacement strategy here, you're also compatible with the traditional approach of deploying a specific model for specific inferencing, and then you can feed the results back directly into your data.
Correct. It's designed to be flexible for your use case. The other thing that I'll point out is you can also write what the video location is, and you can use your SQL queries to essentially track objects across different cameras. So it's not limited to one camera. If you design your setup in a way that allows you to trace objects across cameras by, for example, assigning an ID to an object and then tracing that ID throughout your system, then you can actually see the path that this object has taken through your environment.
That would be fascinating. That's quite advanced.
And obviously you could add to it, John, in your example that there is a rule engine on any EdgeLake instance, so you could just have rules and just push instead of pull whatever you care about.
In our example, where we have the large manufacturing plant, this particular operation is one of the largest titanium smelting operations around, but it also has a very large operation in terms of chemical. So you have different types of readings that are coming back in the various processes, which we have saw very excellent ways of examining the data that's coming back through. But sometimes watching what's going on can reveal things to you that your particular set of numbers didn't show up. So this is a very nice complement to the earlier approach. I can see why they've asked you for the video approach. This is nice.
And one thing, just to make Michelle's comment more clear, it's since we're writing telemetry, the rule engine essentially can look at the telemetry being written, and you can write rules that says if this anomaly was detected, so if you see this behavior, which is a behavior that was written to a SQL database, then do X, which could be maybe alert someone, send someone a ping on their phone or something of that sort. So
Exactly.
It's very flexible and it's built in to work with existing functionality that EdgeLake offers.
Yeah. And by the way, on top of it, we've got the MCP connector, which we demonstrated on the previous meeting. And so this could be integrated into the MCP, and so you could have one AI process which does the identification of the objects and is trained on the specific images that are coming from the camera, but then all the cameras, all the inference from all the cameras are being available to another AI process that doesn't look on identifying the images, but trying to understand what is happening at the plant as a whole and bringing alerts and failures and logic to the organization, not just by identifying images, but from scanning what's going on in the different edge points. Another thing that I want to mention, John, it might interest you. So I was working in the last few days on a diagram how we fit into the industrial plant.
I think that would be excellent. I mean, just for further context, this particular situation, the complex that's going on is multi-company. People have the multi-tenant situation in which we'll need to be able to isolate different operations between multiple companies. So it's kind of two-tiered. It's sort of like you were describing before about having two different systems and yet they're all co-located. Well, the tier one for an individual company and tier two as far as what does the whole plant look like.
I think this setup would satisfy what you want to do there, because when you put a node and you push data, you fully own it. So one company could own, let's say, 20 nodes in their plant or whatever the number is, and then they could decide on each type of data whether they want to share it or not.
Right.
And if you put them on the same network, then company B could share or could have insight into data of type A, but not data of type B. So the granularity of the availability of the data is fully dependent on what the data owner wants you to be able to see. And he could share different views with different participants over the same data, and it could be different from one node to another. So you have full control of it, and you put everybody on the same network, and it's all SQL based. It's really easy to share information this way, and at the same time protect it and make it very secure.
Just for the others here on the call, this situation is that the actual chemical production is dedicated to the individual companies that are going on. So they will obviously want to maintain the privacy and confidentiality of what they're doing. But the electric distribution that's coming is distributed to all the companies. And so you have certain kinds of information where you want to share that are infrastructural in nature, but not share, which are specific, product production type of information. So this is great.